Hello and welcome once again for another ES340 video. This will be day 7, part A, and we're going to be discussing the ideal gas model. So as we left off last time, we were talking about the compressibility factor. And the compressibility factor, we can write it in this form. Z is equal to PV over RT. Now remember, this is not your R from your chemistry class. We're going to have to get used to the way that this book's notation works, whereas the R with a bar over the top is the R from your chemistry class. So just keep that in mind. However, what we're going to then do is we can peel apart what Z is. We can also rewrite this in a different form, right? PV, this is a more familiar form, probably for many of you, but this is going to be times ZRT. PV is equal to ZRT. Now there's a bunch of different ways, and I'm going to write this in different ways in a moment, but basically we conclude that a substance is an ideal gas if Z equal to 1. Okay? When Z is equal to 1, we conclude that it's an ideal gas. What does that imply? That means that PV is equal to RT, right? Because Z is equal to 1. So this is the ideal gas model. Now, this doesn't look necessarily all that familiar, probably. We'll get it into a form, and I'll write it in a couple of different ways so that you can see that, in fact, eventually you'll see that this is, in fact, the form that you're used to. So we can note that V is equal to capital V, where this is the volume, over M. Okay, so that means that we have PV equal to MRT, getting closer to something that you've probably seen before. Or we can do this. We can say this is equal, the specific volume is equal to the molar specific volume divided by the molar mass, which obviously you could read off the periodic table. If it's monatomic, if it's diatomic, obviously you have to multiply whatever the periodic table value of the mass is times 2 and whatnot, but you get the idea. And R equal to, well, that's also R bar over capital M. This is true for all of these substances. So we can get the molar versions by dividing by, or by multiplying these values V, for instance, by the molar mass, right? V bar is equal to V times M, as an example. So if we make this substitution, though, we find that PV bar is equal to R bar times T, again from this formula. All of these are obviously ideal gas as I go along here. I'm just not writing it necessarily in every place, but we're making that assumption. And finally, using the substitution that V is equal to V bar times N, where N is the number of moles, okay, which is something that you're familiar with. Then we can get the following, which is PV is equal to N R bar times T. Now this is your formulation that you saw in your chemistry class. We're not going to work with this very often. You can if you want. You can always convert everything, but I think that that's going to be more work than it's worth. We're not going to use this formulation a lot, but just note that it's the same exact thing as this formulation. It's just now you're using R instead of R bar, okay? And you typically in chemistry class used R bar. Okay, so the ideal gas model comes in the limit, recall, ideal gas model comes in the limit as P goes to 0. Okay, so this is when the pressure is really low, then we can take this of the gas, then we can take it to be like an ideal gas, because the idea there is that the stuff is not packed, the gas is not packed too closely together, so we can ignore the interactions between the molecules. This is all a microscopic scale, right? We only care about the macroscopic, but the stuff that's happening at the microscopic scale matters, and that's what gives us the ideal gas model, allows us to do this. So if there's not a whole lot of interactions going on, you can take it as if there were none, which is what happens when the pressure is very low, and the amount of space that is taken up in the volume by the gas itself is actually really small. That's going to be important. Because each individual molecule, there's no like clumping together or anything like that of each of the individual gas molecules. So both of those things lead us to this ideal gas model. Now, what assumptions can we make? For an ideal gas. Now remember, earlier we saw that if we could make some assumptions when we were talking about a liquid, a compressed liquid, right? We can assume that it's incompressible, and incompressibility led to a bunch of equations, and that's going to be the same thing here. The ideal gas is going to lead us to a bunch of equations. So obviously we need to keep PV equal to RT, of course, but also U ends up being the internal energy, the specific internal energy becomes just a function of temperature, and not the pressure, for instance. Well, obviously, because we're assuming that the pressure is very small, so it doesn't play any kind of role here. So this is why we get this kind of a formulation. Similarly, this is kind of similar to the compressed version, but we can actually take H of T to be equal to U of T plus RT. Why is that? Well, first of all, we said we can take this to be UT, but remember that H is equal to U plus PV, and PV is equal to RT. So this maps this right back beautifully to this equation. So for an ideal gas law, these things are also true. Okay, now you can't take these to be true in general, but these things are true for the ideal gas law. Okay, so let's take a moment so that you can do a clicker question. This will be the first clicker question. For which of the following substances would it be appropriate to consider it as an ideal gas? And you can use the compressibility chart. That's what we were practicing last time, one of the things we were practicing last time. to help you with this, and table A1. That's my hint for you. But which of the following would it be appropriate to consider it an ideal gas? Water at a pressure of 70 bars and a temperature of 311.1 degrees Celsius. Water at 100 bars and T at 311.1 Celsius. Water at 0.06 bars and T equal to 500 degrees Celsius. And water at 120 bars and T equal to 360 Celsius, or none of those. Okay, so let's shift gears now and talk about specific heats and internal energy for an ideal gas. So this is we're still discussing the ideal gas, but now we want to know things about internal energy and changes in energy that happen in an ideal gas. What can we do with that? Well, we already said that for an ideal gas, the internal energy is only going to depend on temperature, and if that is true, then the specific heat is also only going to depend on temperature. That shouldn't come as a surprise, and that piece of it is pretty similar to something you've already seen. But note that these are going to have different equations, so keep that in mind when you're dealing with a substance. Like if you map it back and you find out it's a compressed liquid, you have a set of equations that you can use. If you find that an ideal gas works well for it, or you're told in the problem that ideal gas works, you use the ideal gas equations. Okay, so what does this mean? du is equal to Cv of T dt. Right, that's just rearranging the equation above. So this is again for an ideal gas, but I'm not going to write it at this step. And if I integrate this from T1 to T2, taking T1 to T2 to be my endpoints, then what that means is that I get U of T2 minus U of T1 is equal to T1 to T2 of Cv of T dt. And again, this is going to be ideal gas. Okay, so the idea here is I could find the specific heat, and you could do this, the specific internal energy, which you could find off of a table, for instance, at a particular temperature, subtract that off from the other temperature, and voila, I would be able to map this back to the integral here of this. That's a capital T, by the way, of this specific heat. Now, the specific heat is going to be a function of T, but very commonly we're going to take it to be a constant, which again, if it's a constant, you can just pull that out of the integral, and this integral becomes very easy. If it's not a constant, of course, we have to think a little more. We have to actually perform the integral for one thing. Okay, similarly, we have Cp of T is equal to dH dt for an ideal gas. This is a capital T, sorry. And again, we can do the same trick. We can say dH is equal to Cp of T dt, which means that H of T2 minus H of T1 is equal to the integral from T1 to T2 of Cp of T dt. And again, just like before, commonly we'll just assume that the function here is a constant for many problems that we'll be dealing with. Now notice something interesting that comes from up here. h of t is equal to u of t plus r of t, okay? Plus r times t. Sorry, not r of t. Well, obviously, if I take the derivative of this with respect to t, then I get the derivative of u with respect to t plus r. Again, this is going to be for an ideal gas, so keep that in mind. But this is the equation that you'll come up with. So if I just take that derivative, that's what I find. And what this means, actually, coming from these equations up here, is that Cp of t is equal to Cv of t plus r. Or more conveniently, Cp bar of t is equal to Cv bar of t plus r bar. Okay, so these are the molar versions of these things, and so you'll have units that have moles in them if you are given a specific heat like this. So what does this actually imply, though? Well, you can imagine that, say, if C is a constant, Cp and Cv are a constant, then the difference between them is also constant, or the ratio of them is also constant. As it turns out, it doesn't matter what the equations are. Because of this relationship, actually, they end up always having some kind of constant specific heat ratio. And that's going to be given by K. And we can even actually say something about K. K has to be greater than or equal to 1, but it's not really going to ever be equal to 1. So it has to be greater than 1 because Cp is equal to Cv plus R. Right? So because these two functions are equivalent, just off by some shifted value, some constant shifted value, K is going to be constant, and it's always going to be greater than 1. We can actually rearrange these even more because which will be useful. Again, this is for ideal gas. And it's going to be even more useful if we approach it in this way. We will see this come up in problems over and over again that use ideal gas, that are related to the ideal gas law. So kind of commit these to memory or paper. If you're doing this, you should immediately have these available to you. And I suggest paper probably better because I have a hard time memorizing these as well. But Cp for an ideal gas, and that's true for both of these, it's ideal gas. Cp of t is equal to K times R divided by K minus 1, so it's going to be a constant. And Cv of t is going to be equal to R divided by K minus 1. So the only thing here is the only thing that can be non-constant, of course, is that K can be dependent on T. There is a specific case you can read that in section 3.13 if you want, but we won't deal with that very often, so I'm not going to bother addressing it at the moment. So that leads to the second clicker question. Oops, I scrolled down too far. And that's where we'll leave off. So for this video, upon examination, it is found that a gas has a compressibility factor of Z equal to 10. Should we take the expression delta U being U2 minus U1, or U of T2 minus U of T1, okay, you can think about it either way, equal to T1 to T2, the integral of T1 to T2 of CVD of T dt, be valid in this case? Can we use this, can we assume that we can use this equation is what I'm asking here. That's all I have for this video. Hope to see you again soon.